Okay, so some other things about organic molecules that you might find interesting is what are called isomers. So an isomer is the same molecular formula but a different structure. Okay, so we've been talking a lot about these things where if I just wrote C4H10 out, you'd be like, oh, well, that's this. Well, it also could be this structure here. So one of them is butane, so which is the 4 carbons, all single bond. It has a boiling point, that's what the BP stands for, boiling point, of -1 degree C. Now, you probably have heard of isopropyl alcohol. We'll get to what isopropyl is, but if you notice how the structure here, it's this little V shape. So there's 4 carbons in here. This is called isobutane because of the isomer of it, and so it's just kind of this V shape. If you stick this onto something, it could be isopropyl. So we'll get to isopropyl in a little bit. But this is isobutane, and it has a boiling point of -12. So just by moving that carbon over down to here and putting this shape into here, we change the boiling points of it. So these are skeletal isomers. There's a change in the carbon. Now there is also what are called functional group isomers. So if I put down C2H6O, this is ethanol, and it has a boiling point of 78.5 degrees. But if we put that oxygen in the middle, it's the same formula over here. Now it becomes dimethyl ester, and it has a boiling point of -24. We can also have what are called positional isomers. So this could be like C6H10, so it could be 1 propanol, or it could be 2 propanol. It has the exact same formula here, but where we put the OH group differs into them. Okay, so these are what are called isomers. So isomers, they have the same molecular formula, but they're very different structures. So keeping that in mind. Now these are not isomers of each other. Okay, because it's just they're written differently. So like if I write the chloro group on the side here, or I write the chloro group at the top here, or I drop the chloro group over here or here, it doesn't matter. These are all exactly the same thing. So these are not isomers of it, but this is totally different because now both the chloro groups are on the first carbon and not on either of the carbons. So these are all exactly the same things. These are not isomers. This is totally different, but this is with this. So this and this are isomers of each other because they have the exact same formula up here, but they're totally different compounds. Okay, so hopefully you can see the difference between isomers and other compounds inside of there. But I would bring that up. Okay, so now that we've already kind of started talking about this, I'm going to, again, like taking a little bit of a step back, but now that you've kind of had to struggle through it, we're going to walk you through some of the stuff. So what we've been doing really a lot is nomenclature. We've been doing nomenclature, which is our systematic way of naming something. So what we've been doing, and what you've been working on, is what's called the IUPAC, and this was like the International Association of something Analytical Chemists or something like that, back in 1892, kind of, in Geneva, Switzerland, said, okay, we're going to name everything exactly the same way, okay? Because, as we've been kind of getting at in this class, if I put CH3CH2OH down, well, this compound could be called spirits, grain alcohol, ethyl alcohol, ethyl carbonyl, ethanol, and so it has a whole bunch of different names, okay? And so we have common names, and this will come up really important when we start talking about like when manufacturers make something. Sometimes they'll call a compound a different name just so that they can say they have this special unique thing, and then when you look it up, you're like, oh, it's just ethanol. Oh, okay. So they realized that by having all these different names for it was a major problem. So what they did was they came up with this system. So they have a prefix, you have the parent, and then you have the suffix. Okay? So the parent compound, as we've been talking about, is the number of carbons, right? So that goes in the middle. That's what we've been doing. We've been doing the suffix, which was that. Well, that was where the functional groups go. So that was like if something was an alcohol, an alkane, alkene, ketones, whatever. That goes at the end. And at the beginning is the location of the functional group. Okay? So this is what we've been doing. And so this gives us our parent, our suffix, and our prefix is the location of it. Where is it, and how many carbons? So this is what they came up with for doing that. So one of the things that we've been doing is we've been looking a lot at alkanes, right? So we've been looking at organic compounds. Well, one of the things that you probably have heard the term hydrocarbon. Okay, so what is a hydrocarbon? So hydrocarbon, okay? Well, hydrocarbons only contain carbon and hydrogen. That's it. Okay? So when we talk about the hydrocarbon economy or anything like that, it only contains these two compounds. When we talk about organic compounds, do you remember that from the first lectures? If not, look it up. But so hydrocarbon, it just means that it contains carbon and hydrogen only. That's it. So can we think of some things that have carbon and hydrogen only? So this could be our alkanes, our alkenes, our alkynes, aromatic compounds, and we'll get to what an aromatic compound is, but that's what I've been drawing, the benzene ring. The benzene here, that only contains carbon and hydrogen, okay, in there. So these are all single and double bonds and stuff like that. So this is what a hydrocarbon is, okay? So just to give you some other terms, because, see, organic chemistry goes back a long ways, and so there's a lot of terms that get into it, and so I always like to introduce you to other terms so that you know what people are talking about and when they're referring to things. So when we're talking about hydrocarbons, we're only talking about this. Now, alkanes, what's the special thing about alkanes? You guys remember is that they only have, what, single bonds, right? So let me get back up here. So alkanes were the single bonds ones, right? Well, alkanes, that was our IUPAC name for them. But before that, they were also referred to as paraffins. And so you may see the word paraffin somewhere. If you see the word paraffin, it just means it's an alkane. These could also be referred to as aliphatic hydrocarbons. Aliphatic hydrocarbons is also another term for an alkane. So it's all single bonded in there. Straight chains, they can form singles and stuff like that. They can be straight chains, they can have branches. They all have the general formula of CnH2n+2. Okay, for the straight ones. Now, you can also get cyclic, or cyclo, so cyclic ones. So cyclic cycloalkanes. That's where you draw, say, like a box. There's 4 carbons and stuff like that. They're all single bonded to each other, so it's still an alkane, but we just wrote the word, so this would be cyclo, and 4 is butane. So this is cyclobutane. Okay? So cyclobutane, all of these generally have the formula of CnH2n. Okay? So those are alkanes. So most organic compounds, as you're starting to see when we're talking about these with the butes and everything like that, are really starting to, most organic compounds derive their names from alkanes or parts of their molecules from alkanes. So, you know, that's why we spend so much time on it. That's why your homework assignment was kind of basically on these kind of things into there. So we actually have a lot of compounds when it comes to single and double bonds inside of there. Into there. Okay, so I'm going to take a little side trip here. We're going to look at isooctane, because I always think this is kind of interesting, just because we're talking about alkanes and stuff. So octane. Number. Okay, so octane. We've talked about this before. So when you buy gasoline, okay, you get an 87 or a 94, you know, there's these numbers that are associated with the gasoline, and it's called the octane number. Well, now that you guys have seen this now, you guys should be going, ooh, octane. So it's a single bonded 8 carbons. So the octane number in there. So the octane number, the number that when we increase it, so when you have your engine inside of there, the piston, you spray the gasoline into there, and it sprays because you need to have it in a gaseous kind of form, and then it ignites, and then that pushes the piston down. Okay? So if you just put in normal alkanes, like any sort of alkanes into your engine, you might get premature ignition. So what would happen is, say if you put inside of there, you put in heptane, just straight heptane, like you had a straight chain of heptane and stuff like that, so 6 carbons long. Heptane, it actually has an octane rating of 0, because it's really, this is bad fuel inside of your carbon. So just the straight chain heptane will have it'll cause a lot of premature ignitions, uncontrolled, and things like that. So what it is in order for gasoline to be really good, it needs to have a lot of branches off of it. So what happens is if you've got 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, but I put on another branch here, and a branch here, and another one up in here, this makes for better fuel. So fuel actually needs more branches into it in order for it to be really good for ignition in your engine. So if you draw out 2, 2, 4, trimethyl pentane. So what I'd like for you to do is draw that out. You should be able to do that. So it's single bonded, it's 5, and there's 3 methyl groups in the 2, 2, 4 positions and stuff like that. This compound actually has an octane rating of 100. It's the premier of everything. So if you're getting octane rating of 100, this is the compound. Notice the branches that are coming off of the main structure inside of there. If you do 2,2-dimethyl butane, this has an octane rating of 92. But if I put in 2,3-dimethyl hexane, this has an octane rating of only 71. Okay? And you can notice, what's the difference between these? They have dimethyls, so as soon as we add one more branch, it brings up that. The chains here, so this one only has 4 carbons, this one has 6 carbons, but because it's not as branched compared to its main, like the core of it, it gets a lower octane rating. So what happens is if you have an octane rating of like 90, it means that you can have 10% heptane and 90% isooctane. So what is isooctane? Isooctane is kind of a mix between all these different compounds. So what we really are doing is we have this mix of branched mix is what our isooctane is. So when we buy gasoline, what you're actually getting is isooctane, which is a mix of all these different branched compounds, okay? And the most one is 100, is this one. So what happens is inside of the gasoline manufacturers, what they do is when they break down the organic molecules, so they take the big organic molecules that are coming out of oil, and they're cracking it, so they break up the molecules into these smaller and smaller things. Depending on how the manufacturing process goes and how they do it, they will come up with the different combinations of these different compounds based upon the starting fuel and their procedures, and they will come up with their own combination of octanes, isooctanes. And then with isooctanes, what they do is then they test it, and then they can tell how much it ignites, and they compare it to this 2,2,4-trimethylpentane, and then they compare their gasoline to it, and then they can come up with their octane rating into there. So isooctanes is just a mix of different small chains compounds into there. So we're going to come back into this later on, but it's really not an octane rating. It should be isooctane. isooctanes, when we start talking about fate and transport in the environment, these compounds don't move very far. They're very easy for microorganisms to biodegrade under aerobic conditions. Microorganisms love these kind of things. They're just like little snacks for them in there. They also don't move very far. They get absorbed onto, when we talked about sorption, remember I talked about sorption a little bit? They get absorbed onto the clays and the particles into there, so they generally don't move. Okay, so what happens is when a gasoline spill occurs, these compounds start to get biodegraded very quickly. It turns the aquifer anaerobic very quickly, but these compounds right in here get to be what everybody loves to eat, and they don't move very far. Now, what gets mixed into it, so these things are in there, they're kind of natural. What happens is we get these BTEX compounds, which stands for benzene, toluene, ethylbenzene, and xylenes. We'll get into them, but I keep drawing this compound here, or it also can be drawn like this. This is benzene. Benzene is a no carcinogen. And so this compound, we'll talk more about this, but when gasoline spills, what happens is this all kind of stays behind. It's not very soluble in water. It kind of stays behind. But benzene here is very soluble in water. It comes off, and it's a known carcinogen. So this is what we really focus on when we talk about gasoline spills, not this isooctane. So isooctane, and just so you guys know, like for the federal government, especially the military, all their vehicles have to run on the exact same fuel because they want to have one fuel for the whole thing. Now, what do we do in this country when we have gasoline? We have summer and winter blends. Well, what's happening when we have summer and winter blends is the amount of oxygen that we're adding into these compounds. So we'll talk a little bit later about MTBE, which stands for methyl tert butyl ether, or even ethanol. If we look at both of these compounds, they both have oxygen inside of it. So by adding oxygen into your fuel, it makes it burn cleaner. So we have summer and winter blends because what happens is depending on how these compounds and what kind of manufacturing you have and the amount of alcohols and oxygens you add to it, it changes how easy it burns. So in areas where we have a lot of air pollution problems, they'll change the combinations of how much ethanol they're adding. They'll change the combinations of these because they'll burn differently. And so you can get different blends depending on your winter and summer. So here in Chicagoland area during the summertime, we can get a lot of smog polluted if we have sunlight and you have a lot of these compounds. So we have a winter blend and a summer blends, and so this changes how when we go into manufacturing of gasolines. So one of the things that I'm hoping you're seeing from all of this is it is kind of specific to the manufacturer. So if it's a BP versus Citgo, they're all going to have their secret way of doing these things. And so it forms a fingerprint of the compound. So say like Citgo gets their gasoline from Venezuela. They use Venezuelan crude at Citgo. A Venezuelan crude is going to be very different than, say, a Middle Eastern crude versus a U.S. crude. They're all going to start off from different compounds, different organics. We'll talk about formation of gasoline later on in this class because it's kind of important for you to understand it from an organic compound. But they all start off with different starting products. There's different amounts of aging that go into them and everything else. And so where they're from, how they're manufactured, as I was talking about with isooctanes, will come up with different fingerprints for each different types of gasoline. So gasolines can actually be kind of fingerprinted as to what goes into them. So hopefully that was kind of interesting for you to know a little bit more about what you put inside of your car.